I'd like to introduce my Brenden colleague, Arda Gozen. We've been collaborating for quite a while on bioreactor for cartilage work, and now we're extending that to T-cell production to make cells that fight cancer. Brendan's been working on that. You've probably seen his poster and talked to him. And so they're going to give us a presentation today.
Thanks, Bernie. My name is Arda Gozen, just like Bernie introduced. I'm a mechanical engineer, and my focus is manufacturing technologies in general. And again, we've been collaborating with Bernie on biomanufacturing aspects, which is one of the newly emerging manufacturing paradigms. Again, as a mechanical engineer, I think I'm a little bit different from this crowd here. Do we have computer scientists all around? Everybody? Anybody who's not electronics? Nobody? Well, so the manufacturing research or manufacturing technologies in general, in the industrial perspective, up until like the last decade, we've been mostly in the operations technologies domain. So you might have heard the concept of an OT and IT in a company, and they don't like each other so much, right? And operation technologies is what's happening on the factory, on the shop floor, where products are being created and manufactured. And again, up until the last decade, that has been pretty isolated from information technologies, or at least they didn't kind of come together as much as possible. But so what we're seeing right now in the industrial reality throughout the globe is that so what we call the Industry 4.0, the fourth industrial revolution, is sort of going on. In the United States, a little slower than Europe and some other countries, but it is definitely taking over. And the main idea behind the Industry 4.0, the fourth industrial revolution, is that manufacturing operations are becoming essentially more data-driven. Manufacturing machines, systems, enterprises are all networked. They make use of these advanced, information technologies like machine learning, Internet of Things, cyber physical systems, more and more and more. And the projected and actually realized gains in the levels of production and the production performance is enormous. So it's one of those things that are one way or the other, sooner or later, is happening to each manufacturing enterprise in the world. So we have to talk about them. We have to address them. And that sort of was my gateway to sort of this community. And as you can imagine, once you have your devices connected to networks, sharing big chunks of data, then generally in the manufacturing domain, it's about the production method, what's going on with your manufacturing operations, the performance data, product data, and by obviously using data analytics, machine learning, you can learn and optimize a lot about your manufacturing process. As you're getting these benefits, obviously, right, you're opening your operations up to the internet, and also you're making yourself vulnerable to cyber attacks. And the amount of money that we're talking about in big manufacturing operations is enormous. And there's quite a bit of motivation to, attack such enterprises, attack such big operations. So cybersecurity becomes a huge deal in manufacturing research now. And in manufacturing conferences, we generally talk about machining and how we cut materials, how we 3D print materials. And all of a sudden we're talking cybersecurity, we're trying to understand what it all means, right? So this is sort of a preamble to what we do here. As I said, our focus is biomanufacturing, which is slightly, again, different product than the conventional sense in manufacturing. We're looking to create cell lines. We're looking to create biomaterials with high throughput that can be used in medical applications. And bioreactors are, in my perspective, at least, manufacturing systems that are used in that regard. So we're going to basically look at some sort of a case study here. How would you basically design this biomanufacturing system? How do you generate, again, this is a buzzword, but it's used. How do you generate a digital twin of a biomanufacturing system, which is a computer simulation, basically? More importantly, right, can you use this digital twin architecture to simulate potential cyber attacks to that system? Also sort of prototype mitigation strategies and essentially see everything in the simulation domain. And we're gonna at the end talk about how do you go from simulation domain to real life application. So I'm gonna leave the floor to Brenden here, who's gonna give you guys a little bit of a background because he's a lot more knowledgeable than I am when it comes to the fundamentals of the bioreactor system, what's going on in there physically so that you have a much better sense of the real life application. Brenden.
Yeah, so everybody, my research area is in chemical engineering, so a little different for most of you. But today I want to give you first a little background on biomanufacturing and as Arda was saying, why it's very important to have these systems and the data that's all online for these systems, especially for kind of the next generation of biomanufacturing. So first of all, for those who aren't familiar with biomanufacturing, this is a huge industry. And basically in this industry, they're using biological systems like different cells, plants, tissues to produce valuable products. So that could be like food products, medicines, agriculture, energy, a lot of different applications. This is a huge market. It was worth 19 billion in 2020. That's expected to go up to 85 billion in the next decade. So 15% growth every year. And a lot of the issues that we're facing in the future can be addressed by this industry. Medicine, you know, the availability of medicine, the crisis with water and food, availability of those, climate change, and then developing new sustainable energies. And with biomanufacturing, especially with shift toward more automated online operations, there's been a concern with cybersecurity. And so in this industry, there are a lot of different stakeholders. You have like the healthcare industry, hospitals, you have governments, you have private companies. All of these institutions are using biomanufacturing to produce products, and they're handling a lot of sensitive data. So anytime there is a cyber attack on manufacturing systems, it can interrupt production. For example, in COVID-19, if there's an interruption for like production of a vaccine, that could interrupt the response to the pandemic. There's a lot of sensitive medical data that's stored in systems used in hospitals, companies that are manufacturing medicines. And so if that data is compromised, there's potential for information, you know, being that's private, that's being leaked out to the public, but also there's a lot of financial implications. And for the last 10 years or so, it was found that there were 10% increase in data breaches in the healthcare industry, specifically each year. There's been a lot of recent incidents where attempts were made to steal IP, sabotage manufacturing systems and industry. And kind of one example I can show you is this company, Merck. It's a large pharmaceutical company. And in 2017, there was an attack attempt made using this ransomware. And what it did was it permanently encrypted data on their computer systems. And this was part of systems that were all connected to their manufacturing operations. So it really shut down a lot of their manufacturing operations. And the facility that was affected the worst was a vaccine production facility. I believe they were making vaccines for HPV and hepatitis B. And since they had such a huge shortage of vaccines from this interruption, they had to borrow from the CDC, the government stockpile of vaccines. And so this company was losing a lot of money, and in addition, the government was losing money. So this attack, all in all, it caused about $1 billion lost by all the parties involved. So as you can see, any cyber attack on these biomanufacturing systems can be really expensive. They attributed this attack to Russian hackers, but they didn't find any evidence that this company was specifically being targeted. So it could have happened to any company, really. And as we look at the future of this industry, and as Arda was talking about, all the shift towards kind of online operations, there's going to be more attacks. There's going to be more specific targets in the future. So changes need to be made to the current levels of security that are being used. The old standard in this industry was to use a lot of large-scale equipment, such as bioreactors. So bioreactors are basically a system that you can use to grow cells. If you want to develop a medicine, the cells can produce like a protein or something like that that can be used in medicine, and it does it on a large scale. But with all these large pieces of equipment, they're all very vulnerable to any kind of attack because they're all streamlined connected. So if there's any kind of interruption, then of course you can have shortages of medication, and not just in medicine, but in other agricultural industries and food industry applies as well. So in the future, I'm expected that there's going to be a shift towards smaller systems, ones that are more flexible, ones that are more automated. There's also a shift in the healthcare industry towards more patient-specific therapy. And so with these new systems coming onto the market, there's going to be a need for new approaches to cybersecurity. And with all of these new systems, and especially network connected systems, which allow remote access, allow better handling of data, this introduces new vulnerability. So we have to change our design approach. And so what I'm going to show you here today is kind of an example of this that we've been working on in Dr. Van Lee's lab. And the system that we have here is the centrifugal bioreactor. So this is kind of an example of a smaller scale, more next gen style of system compared to the larger scale systems that have traditionally been used. And the centrifugal bioreactor, you can see it here in action. Basically, this is a small bioreactor that uses centrifugal force to expand cells. And the main application for this system is in T-cell treatments. So cancer immunotherapy is a type of cancer treatment where you're using a patient's own immune system to treat their cancer. So instead of like radiation, you just take their T cells and you modify them in the lab, and then you need a way to get them to grow so you can have large numbers of them. And that's what the bioreactor is for. And traditionally, since this is a relatively new area in the last decade, it's very expensive, and the processes that they're using are pretty slow. So we're developing this system because it has potential to lower these costs, and it's so far, while we've tested it, it's more efficient than the current standard that's been used in industry. And how this system works is you can see this circular part is a centrifuge disc. And so on the centrifuge disc, you have this chamber right here, and that's where the cells are. The cells are being grown inside the chamber. And while this is spinning, you have tubing that's pumping medium. Medium is basically has all the nutrients from the cells, and that's going continuously through the chamber while the centrifuge is spinning. And because of this unique design, there's actually a balance of forces on each cell in the system. And this is kind of the key engineering principle of this system. So if we look at the chamber up close, and we look at just one cell here, on each cell you have on one direction, you have centrifugal force, which is from the spinning, and then the other direction you have drag force and buoyant force, and that's from medium flowing through this chamber. So while this system is operating continuously, there's this force on each cell, which basically holds each cell in place and allows you to get up to a really high density. So you have a really high concentration of T cells, which you need to fight cancer that are growing inside here. And with this system, we have specific ways that we use to optimize it. And this is how we've been actually working and developing our prototype, is using mathematical models. Our mathematical models are shown here. With this model, there's 4 main equations. This is kind of the main equation, and then there's 3 equations that go along with it, this differential model. And there's a lot here, but what the important part is this C cell represents the concentration of cells and how that changes over time. So we can predict how many cells there will be over time based on different parameters. And the 3 most important parameters here, each kind of correspond to an equation. So glucose is the first one. Glucose is the main nutrient the cells need to grow, and that corresponds to this equation. And then the next one is lactate. Lactate is something that builds up over time. The cells produce it as a byproduct when they're growing. If you can think of lactic acid, it's something we produce in our blood when we exercise. And lactate can harm cells over time. It's actually toxic if it builds up too much, and that corresponds to this equation. And then the last one, which is important, is ammonium. And like lactate, it's something that can build up and can harm the cells. That goes with this equation. So these 3 things, glucose, lactate, and ammonium, these are what we really want to control in this model. Because if we can figure out what the ideal levels of ammonium and lactate and glucose is, then we can produce an optimal cell density. And to solve this model, you can use a run-kata method. And we've done that in MATLAB. And I can show you some results of the model based on just some initial assumptions. So the model, as I mentioned before, we start out with the cell concentration. And so this is looking at 500 hours, how we basically start with 0 cells, and then over a period of time, this is how many cells you would have after 500 hours. And while the cell concentration is increasing, because the cells are growing, at the same time, CG, glucose, is going down because the cells are consuming all the glucose. And at the same time as that, the ammonium, again, a toxic byproduct, is going up because as the cells grow, they secrete ammonium. And then lactate, similar to ammonium, it's increasing as the cells are growing. So when we're looking at these main parameters, we want to have a way to control them in real time. So we need a process control system that can monitor the levels of glucose, ammonium, and lactate. And essentially, if there's a drop in glucose, the system can then introduce more glucose. If there's an increase in ammonium or lactate, those can be filtered out. And we can restore the ideal operation, which is the ideal environment for the cells to grow in. And so to develop a control model, we've been using MATLAB Simulate. And this is kind of the next phase of the project now that we've developed our prototype. And as I mentioned, it's critical that we can monitor the levels of glucose, lactate, and ammonium. And We can also introduce other parameters that we want to monitor, such as oxygen available to the cells, the pH, which is the level, how acidic the basic medium is. But we've started with glucose, lactate, and ammonium. And the other big aspect of this is the possibility of cyber attacks. So with an online system, it's really valuable because it allows you to control it remotely. You can also more easily work with the data for this system. And you don't have to have like a technician operating it constantly if you're able to remotely. But this introduces the risk of a cyber attack. So with our model, we've also simulated the effect of a cyber attack or an interruption to the system. And so now we're going to do a demo of this in MATLAB, and I'll leave it to Gozen to take over and show you that.
Leave the slides up. I'll
Yeah,
go back to. Sorry, I didn't want to.
Yeah, but that's the last slide, but I'll just leave it open for questions before we move on to the next part.
Any general questions? So once a cell reaches full maturity, there's shelf life to it, where does it have to be?
Yeah, there's definitely a shelf life. So with these cells, there's a specific time frame. Usually it's about 2 weeks or so for the traditional process to grow these cells, and that would happen right before they go into a patient for treatment. But with our process, we're hoping to cut that down to about a week. But this is something that would be often done in a hospital. They have a system like in a cancer center where they're growing cells, and so it would all be done in a short frame of time, like goes directly to the patient after the cells are manufactured.
And you're using glucose as basically
Yeah.
cells grow. You try sugars.
For these cells, glucose is what they need to survive. There are a few other, not sugars, but I guess I would say metabolites. So like different things that are present normally in the blood that cells, especially like in your immune system, need to grow. And with our process, there are a few other things that we have to add. There's this, it's called interleukin-2. It's basically part of your immune response. And whenever you have like if you get sick, it's something that these cells need to grow right away at the start when they're responding to an infection or something. So that is something that we may look at in the future. Yeah.
So if you go back to the equations, Brenden. So Brenden talked about a real-time control, right? I mean, again, conventionally systems like this could be operated completely manually. And these operations, from the system's perspective, are extremely slow. So you're looking at a lot of days for cells to grow and reach a certain number and all that. So you can put someone in front of it, gradually come in and check these levels, and take necessary actions to ensure that the bioreactor is operating in a sufficiently efficient manner, right? So to substantialize this a little bit here, one thing that's traditionally done, for instance, monitoring of the glucose levels, and if they are below a certain amount, that's going to inhibit cell growth. And so you may want to increase the concentration of glucose that's circulating in the system. So you see in these equations, these constants of CG0, for instance, so that's the concentration of the fresh media, how much glucose is there in the fresh media that can be introduced on command through the circulation. So whenever the glucose amount goes below a certain level, that's monitored through a real-time sensor, you can increase the flow rate of the fresh media, right, into the system, and that would up those concentration. So that's something that's generally done. And when you need to automate the system so that you don't have to have someone monitoring the system all the time, you have basically this control system that can do this very simple control operation. Obviously, you can go a lot more complicated than that. I mean, you can sort of use conventional control systems methods to forecast these changes effectively and then really be proactive and get the system to an optimal level. But today, I want to simulate a scenario where it's, again, super simple. We have this system. The system is trying to make sure the glucose level does not drop below a certain threshold by intermittently increasing the flow rate of the fresh media into the system. So, and then we're going to simulate cases of, well, if this system is attacked somehow, so that the glucose reading is actually, that is transmitted to the control system is actually not accurate. It misleads the control system in a way that the system thinks everything's fine, right? So that will lead to issues with the production and which may be overlooked. Now, before I jump onto MATLAB, anybody here used MATLAB before? Can I say show of hands? Yesterday counts. So it is a more of a tool. It's not really a programming language. I mean, yes, we do a lot of programming at somewhat high level like Python, really, but it has many additional application-based tools that help a lot of engineering applications. So, and Simulink is sort of a sub-tool of MATLAB. It's a graphical programming language, and it's really powerful when it comes to simulating physical systems like that and integrating that with algorithms and seeing the interplay, which is exactly what we're going to do. So let me go ahead and jump there, hoping that everything will be working. All right. So, okay, so let's see. Let's start. So again, this is kind of complicated if you have never used Simulink and MATLAB before, but this is the general idea. You have these different boxes, and each box might run a simple mathematical operation or a more complex operation, and you can embed algorithms inside your code and inside your simulation, essentially. And if I double click on one of these, you'll see, basically, you're going to see the code being written and interface with the rest of the simulation through inputs and outputs that are going into this function, right? And coming out of this function, going back into the simulation to be just like, this sort of a black box right there. So that's the general sense of it. So now with this simulation, by the way, there's not a synchronous practice here. I'm not going to ask you guys to do anything, but I just want the code to be in front of you in case you want to play with it during the session or after. And so having said that, if you sort of break down this mess of a simulation there, so the first block that I want to look at is here, and this is sort of the black box representing the physics of the system, captured through those equations Brenden just showed you. So I'm going to click that and double click on that, and that's going to open up another mess of a network. So, so there were 4 differential equations that sort of dictated that the behavior of the system in the earlier presentation. So if I pull that back up, so the first equation here tells you basically what is the rate of growth of cells, right? The second, third, and fourth equations, what is the rate of growth of glucose, ammonium, and lactate. So when Simulink is running, in most cases, what's happening is it's running this differential equation solver in the background, right? And basically solving these equations numerically and predicting the behavior of the system accordingly, right? So that's basically your dynamic system simulation. So the box that we are on right now basically is 4 of these equations, and the equation pertaining to glucose is actually right here. So some of the constants, so just to break this one equation, I'm not going to go into each of them, but so you have D here is the dilution rate. It's basically a function of the flow rate of the fresh media, concentration of the glucose in the fresh media, the current concentration of the glucose. This is a yield constant, basically the amount of glucose consumed by the cells per unit cell growth rate, right? So that's obviously going to subtract, so it's going to reduce the glucose concentration, basically. So so we're simulating this equation right here through these boxes. You have multiplication. So you have basically the rate is calculated right here. This box here is a numerical integration, right? So if you have the rate of glucose, you take the integral of it, it's the current concentration of the glucose. So it's fed back into the equation. You take glucose minus the current glucose minus the initial value of glucose, which is coming from your fresh media, multiplied with the dilution rate D, and then that and subtracting from that is the consumption of glucose coming from the cells, and you get to the rate itself. So you have this feedback loop that represents the differential equation that's right here. So we have, so if you look at the simulation, we have basically all of these different equations. So one here, one here, one here, lactate, ammonium, they're all captured. And then with this big box, you have the cell growth. And the reason this is done through this piece of code right here is because it's a nonlinear expression. I find it much easier to just code the equation, right, than just, try to construct it with the blocks. And then you can do that. And the main idea here, by the way, is, in the cell growth, you have the ammonium concentration, lactate concentration, glucose. So as the amount of lactate increases in your system, right, so that is going to inhibit the growth rate of cells. And if it reaches a certain amount, the growth rate will technically go down to zero, right? So we're capturing all those nonlinear relationships inside this function, and it meshes very well with the rest of the simulation. And one important thing to note here, again, going back to the equations, so you see the cell rate goes into glucose, right? And it also goes into ammonium and lactate, and ammonium concentration feeds back into the cell rate calculation, right? So there's a lot of interplay between these equations, which makes the system of differential equations. And again, if you look at the simulation, all these connections are made very intuitively through these, data links. So the output of this box, again, this is too complicated. Don't worry about it. Just get the main premise of it. So the input of this box is F here, which is the flow rate of the fresh media. Okay, that's pretty much the only input we're simulating right now. And the outputs are cell concentration at any given time, glucose, ammonium lactate. We also have what was CAMB? Yeah, so this is sort of a byproduct of this particular operation that we're not focusing on today, but it's something else we can simulate. So I go back to the higher level simulation. You can see all of those outputs actually right here. Now you can take these outputs and use these to integrate with your control system that you want to simulate, right? The idea was, okay, well, if I monitor the glucose concentration, if that goes below a certain level, I can take action to up the flow rate of the media to increase the glucose concentration back up to, hopefully a desired level, right? So it's obviously a dynamic process. Once you up the glucose concentration, the cells are growing faster, they're consuming faster, glucose will start dipping right away. So a bunch of things that we're not, obviously this is a very simple simulation after all, right? We're not simulating a bunch of real life stuff here, such as Brenden talked about the capacity of the bioreactor. So you can imagine that eventually cells will populate those chambers inside the bioreactor, and they will need to be removed and essentially used, right? So that capacity is sort of a saturation. We're not including it in there in our simulation, just to keep things a little simpler here. And there's concept of cell death that that may significantly increase with the concentration of some of these products. But we're not really including there here. But again, infrastructure is there, right? So once you get the simple simulation running, it's quite modular. You can keep adding on to it. But in any case, so we wanted to simulate it and integrate this control system, as I was mentioning, and that control system's right here. So if you sort of track some of these wires, so I have scopes here which can, in real life, and not real life, but in simulation time, basically monitor each of these outputs as basically in terms of plots. So if I double click on one of these, so this is one of the scopes that we're going to work with. So this is the yellow here is the concentration of glucose as a function of time in hours, and blue is the sort of the false concentration of glucose. We're going to get into these in a minute, just to show you what scopes look like. So the idea here is to feed the glucose concentration as well as the current level of flow rate, along with the lactate concentration, the volume of the bioreactor, which is a constant, and then and then a minimum threshold information below which we don't want to go into this control system. So this control system was originally designed to be multifunctional in a way that, so you take an action basically if the glucose goes below a certain level or lactate goes above a certain level, right? So that can be another control consideration that may be making. So if you're measuring byproducts, right, you can say, well, okay, if the byproducts went above a certain level, we want to replace that byproduct with fresh media, right? If you go back and look at the equations, if you increase the dilution rate here, that will essentially have an effect of reducing those byproducts, sort of cleaning it up, flushing it off the system, so that cells can grow a little bit better. So, I mean, obviously everything's interconnected, but again, to simplify, we only change our control criteria to, well, look at glucose. If it's below a certain level, increase the flow rate basically by, by 5, whatever units we're working with here. I think meter, is it milliliter per minute? So we're upping it by that constant amount. Super simple, probably the not smartest control algorithm we're working with here. But again, we're trying to just demonstrate the functionality. And if that is not, if the glucose level is okay, right, just pass the flow rate as is, don't change it, right? It's a very, very simple algorithm. And that is our simple controller. And then that goes back and updates the flow rate variable here. So just a little bit of a detail. So if you worked with MATLAB before, MATLAB has this thing called the workspace. You can monitor all your active variables that are running or that has run, worked with your code, and you can manipulate with them even if your code is not running between the runs of your code. Simulink has its own workspace that you have to manage as a separate memory. So these boxes are basically memory elements inside the Simulink. If you want to pass information from one corner of your simulation to another, you can use these gateways if you will. And that's what's happening. So that flow rate is fed back into the system, right? And it generates new outputs. So as I said, the entire simulation is basically a differential equation solver, right? So just to show you, right-click model configuration parameters, you can set some of the solver controls over here. So let's see, it's taking a while. You can select your differential equation solver. You can leave it to MATLAB, which is generally good. You can set, you're gonna obviously numerically solving differential equations, you're going to discretize time. You can do fixed step, variable step. You can set your step size and start time and time, and it will basically do these calculations and output all these outputs from the simulation as a function of time and plot on those scopes as I showed you. So that's sort of the very basic of the simulation. So now I'm going to get into the details of it and simulate some cases just to give you an idea without even getting into cyber attack. There's a bunch of initial variables that needs to be input into the simulation before we run the simulation itself. And the way I do that is through this MATLAB code. And all these initial variables are sort of dumped into my workspace. These are those constants of the glucose yield constant, right? Initial concentration and all that good stuff. And there's a bunch of control variables that I'll be playing with here. But for now, I just want to show you the case where there are no cyber attacks. Everything's working perfectly. So if I run this code at the very last line here, it essentially goes ahead and runs the simulation itself. So we're going to see all the simulation scopes being updated here. So let's see if we get situated over here. Go some of these using. So I'm going to go ahead and run this code. Let's hope it doesn't take a whole lot of time. But as you can imagine, I mean, this is quite. There's a lot of metadata going in the background, running on Windows. This is going to be a slow run one way or the other. So let's see where we're at. So it is running. Let's pull some scopes here. So one of them is, well, what's our cells doing, right? So you can see, again, the x-axis is hours. Obviously, it takes much shorter to simulate hours here. So that your cell concentration is exponentially increasing, which is what the model dictates. Again, there's going to be a limit to this, which we're not capturing in the simulation. So let's keep updating this. So the glucose was right here. So for now, just focus on the yellow curve. That is the actual glucose concentration. And then we set the threshold concentration of glucose as 100 here. So the idea is that we have a starting flow rate. With that flow rate, the cells are growing exponentially. So the consumption of glucose is ramping up. And once you hit 100, right, the control system kicks in and ups the flow rate of the fresh media. But again, cells, there's no limit to what cells can do in this sort of primitive simulation. So cells keep growing, and then glucose is being consumed still. And then the control system ups it again. But the amount of cells are even higher now, right? It's exponentially growing. So that action doesn't help as much. So you need to take action in earlier and earlier every time. Again, you know, after a certain period, this becomes non-physical. But again, we're making a point, right? So I'm gonna let this simulation finish here and maybe show some other parameters. So I have lactate. So as the cells grow, you see the lactate amounts going up. But every time I introduce a higher flow, I increase the amount of flow rate into the media. It dips down just a little bit because I'm flushing the amount of the lactate from the circulation. But it goes up because cells are growing even faster, and the number of cells have increased, right? So again, just like glucose, it's sort of jumping up and down and saturating at a certain level. So same goes for, let's see, I think, yes, this is my ammonium. There you go. So very similar behavior, obviously different numbers here, but the equations were pretty much identical, right? Mathematically, the byproducts are doing pretty much the same thing. So, so the next step would be, so let's assume again, this is some sort of a computerized control system. The glucose reading is inputted into this data acquisition system, interpreted, and the actions taken and automatically that opens up the valve to introduce the flow rate of the fresh media, and everything's happening. And then let's say Brendan's running the system here, and he doesn't want to be in front of the bioreactor because it takes days and days. He has other stuff to do. He's monitoring this through some sort of Internet of Things implementation, right? And seeing the data in real time from his home computer connected to the WSU network through VPN. But then, somebody hacks into the system, right? And again, wants to mess up with these glucose readings. So I'm going to simulate that. Again, don't judge me if my idea of a cyber attack is extremely primitive and kind of dumb. But again, I'm trying to make the point here, right? So what I'm thinking here is I'm trying to get into the mind of the cyber hacker here. So the attack algorithm is going to take the actual reading of glucose, okay? And is going to take the minimum threshold that the control system is working with and scale the reading of glucose such that its trend is actually maintained. So if Brandon's just watching it from the side of his eye, the shape of the curve of glucose looks going to look very nice, right? But it's scaled in a way that it will never go below 100. So instead of being between a max level and 0, it's scaled such that it's max level and 100. So it's never going to go below 100, which is never going to trigger the system. But the trend is looking nice, so everything's hunky-dory, but it's not the case, right? So let me show you that implementation right over here. That's the workspace. So then how do I? Oh, this is yeah. Right, so I'm gonna keep this on. Okay, so that box is right here. I'm going to show you the implementation. So again, it's taken in the current glucose concentration. I'm calculating the rate of glucose, actual glucose concentration. There is essentially a constant here cyber attack if it has kicked in or not. We're going to kick in the cyber attack the first time the control system actually takes action. I have a time variable. What was T0? Oh, so that's again an internal variable that we're using, and some constants that go into the scaling algorithm as I'm updating with the simulation change. So if you look at the algorithm, here's a bunch of if statements. If the cyber attack is kicked in, looking at the rate of glucose. The rate of glucose is increasing or decreasing. So the algorithm itself is trying to figure out the right time to kick in, okay? And again, you can write any code here. I know actually, if you don't want to code in MATLAB, I know there are interfaces where you can code in a different platform, sort of integrated with Simulink. I've never done that, but I know it's available. So you can prototype any sort of intelligent cyber attack algorithm right here, like this. And eventually, once the attack kicks in, there's basically this scaling math that's going on so that the false glucose reading never goes below 100. So now, this is MATLAB. Where did it come? Oh, there you go. So, okay, let's go back to this. So in order to simulate it, I'm going to go back to my code. So I have this control variable attack. So I'm going to turn that to 1. So that's going to basically add that code into the loop. So just to show you where that is. So I have attack is right here. So you have the sort of switch. If the attack is 1, which is coming from the workspace, it diverts the attack signal into the control system. Otherwise, it takes the real signal. But so you can do flow control very intuitively, just like this. So, so let me run the simulation like that. So it's going to sort of reset in a minute. There's a lot of initialization that's going on. So now blue is the attack signal, yellow is the the actual glucose signal. And then the cyber attack kicks in the very first time the control system actually takes effect, right? So it goes to 100 up until 100. So let me try this. It's all the same. And once the cyber attack, sorry, the control system kicks in for the first time, you see the deviation starting, right? So the blue is the attack signal, yellow is the actual signal. And for now, everything is fine, really. Well, to a certain extent, but the error is obviously growing. And once we normally hit 100, you will see that the signal is still above 100. So the control system will not kick in. So again, taking a while, I wish there was a fast forward, but again, so many computations happening in the background. Running in the workspaces, I don't think it helps. But as this is running, let's talk about the next step. So, well, okay, so you're simulating the cyber attack. Obviously, you want to do something about it, right? There's a plethora of algorithms and approaches that are introduced to sort of mitigate the attack at this very end level, right, at the process. And that obviously starts with detecting the attack, right? Looking at the sensor readings that you are seeing and figuring out if they make physical sense or not. And again, depending on the physical system you're working with, the quality, complexity of the attack, it may be a very difficult task. So there's a lot of work, obviously, that's going to go into figuring out the best algorithms to mitigate it. So, by the way, it crossed 100, but the control system couldn't kick in because the system is thinking this is the actual glucose, and it will actually never kick in, right? So that may have detrimental consequences. So, so here, I'm sort of prototyping a very, very simple algorithm to sort of mitigate or at least detect if there's a cyber attack or not. And the idea that I'm coming up with here, again, this is a simulated system. I know what physics is going into it, but I can do this in real life too, and then those equations will not be exactly accurate, obviously. But again, I can use this algorithm that I can use this thinking that all these, rates of different constituents inside the media has to follow these laws that are given by the equation, or at least somewhat, right? So if these trends are violated to a certain extent, I can turn on a flag and say, well, it doesn't make a whole lot of sense. Something's going wrong, right? And we're not getting into sort of eliminating the attack and coming back to the normal operations. But this is just, okay, here's a flag, it's a cyber attack, do something about it. So we're sort of ending it there. So to show you where that happens, and I keep clicking over. So that's, again, a very simple so attack detection's right here. I'm going to look at this code. So what this code does very simply, takes in the rate of change of glucose along with, again, we're assuming that we can monitor not only glucose, but we can monitor lactate. So taking a whole bunch of current reading related variables here, rate and actual value, along with initial concentration and dilution rate, the amount of fresh media pumped in and current concentrations. And basically what this algorithm does, again, very simply, predicts a cell growth rate, looking at the amount of lactate and the rate of change of lactate, going back to these equations. And using that, right? So you have this, you have this, you have this, you have this, you calculate this and feed that back into this equation. Everything else, you calculate the rate of change of glucose. So that's sort of a prediction. If that prediction deviates significantly from the actual rate of change, then you say, okay, wait, something went wrong. And obviously it's going to work perfectly in the system because the system already is following these equations to the T. So let's see. maybe with the current simulation, I can show you what I'm talking about. Wrong selection there. So I have this sort of inline scope. Huge initial error. So this signal that's coming out of this mitigation algorithm is basically a quantitative value of the difference between what I expect from the system and what's really happening in terms of rate of change of glucose. And a difference of 0 means exactly what's expected, no cyber attacks. And a high number means there is a discrepancy, right? So you can see with the cyber attack turned on, discrepancy starts from 0. This is the moment where the first time the cyber attack kicks in, and then the value goes up and saturates at a certain level. I mean, that's basically how the system works. Now, so you can say, okay, great, wonderful. So this will work in a simulation. What's going to happen in real life, right? So obviously I can make my system more complex and all that, but we can mess things up a lot more easily by just adding one real life fact of doing measurements and running experimentation, right? What could it be? Any ideas? Like when I'm reading a CySER reading, I'm hoping that it tells me exactly what the concentration of glucose is, but what do I have to deal with? Even if it's just, just plug in everything, I'm reading a value. What may be misleading me, even without any cyber attack, anything, natural operation, any experimentalist in the crowd? Any ideas? Anybody use the sensor?
The question is, what misleading you before you had the cyber attack?
Yeah, I mean, you just, it's a perfectly operating sensor. Like this, let's say you have an analog reading, you're getting an analog signal out of the sensor. What will be misleading you a little bit at each time point that you're reading the signal? Noise, right? There's never zero noise situation. There's always some noise into your system. There's going to be some distribution of noise around your signal. It may be minute, right? But it is there. So let's say you want to see if you have an understanding of what your sensor noise is, and some manufacturers will tell you that, right? You can implement that in your simulation. So this is what I'm doing here, just to sort of test if the sensor noise is an important factor when it comes to detection of the cyber attack. So I have this very primitive algorithm, seems to be working when everything is perfect, right? So if I go ahead and add this sort of, you can see there's a band limited white noise box that you can pull from hundreds of different sub functions that Simulink provides to you. Double click on that. You can set up essentially the power of the noise and some timing variables, some randomization seeds. You can customize it in any way you like. And what I'm doing here is if this noise switch is turned on, right, I'm adding this noise into glucose signal, or I can add it to the lactate signal, right? And I'm going to really add a tiny bit amount of noise. So if I look back into my code, so my noise variable is right here. Okay, I'm just going to go ahead and turn that on. And then I'm just going to turn off the attack button, because if you have a cyber attack detection algorithm, you better make sure there are no false positives. Your system shouldn't be flagging you when there is no cyber attack. So when I do this, I'm expecting that that difference is going to be still at a low level, so that I'm not thinking there's a cyber attack. So we go ahead and run this. Look at some of our readings over here. So again, this was my glucose concentration. Right? So let's see what it's going to do. So there are no cyber attacks here. So even though the blue is still the attack number, but it's not fed into the system. The system is actually seeing the yellow. Now, again, take my word for it. This is not a whole lot of noise, and I'm trying to zoom in to give you a better picture, but oops, latency is getting me here. But you see, there's a little bit of an oscillation around the signal, and this is quite realistic. This is what your readings kind of look like, right, in a real life system. So now let me go back and check what my cyber attack detection algorithm is doing. So that difference is supposed to be 0. And to go a little further, I can say, okay, well, that different signal is above a certain threshold. I say there's a cyber attack. So let's see what that signal is doing. So here, look at that. So and you see actually how terrible was the initial idea was, because it's using rates of changes, right? So when you have noise signals, even if the signal is changing a tiny bit, it's going up, down, and the rate of the signal is oscillating all around the place, and that's what you get. So if you threshold the signal to detect the cyber attack, it's triggered 10,000 times, right? So if you, again, just to save time here, if you run this with the attack on, it will be indistinguishable from the signal. So this algorithm is not going to work. Well, what can you do to mitigate this, right? So in real life, if you want to process your signals coming from analog signals, analog sensors, you want to add some sort of a filtering, for instance. So I haven't integrated into the simulation yet, but just to show you that it is possible, I'm going to library browser here where you can get the wealth of available boxes that you can use. And it's going to take a finite amount of time to open. You can say filter, search it here, see what we can get. I mean, obviously, these are sort of standard filters that you can implement and with their discrete transfer functions and so on and so forth. If you're familiar with system dynamics or notch filters, low pass, high pass filters, drag and drop and prototype it, right? So you can do that. You can see, then tweak your algorithm, prototype everything perfectly without going to the experimental system. Kalman filters and everything, you can do all that. So in your simulation, there's another sort of nonlinearity and complexity that I added. So even if you don't have noise, let's say, or noise is like small enough so that it doesn't mess up with your algorithm, this algorithm uses 2 different sensor readings, right? So lactate and glucose. So again, when things are perfect, the lactate and glucose are updating, coming from the physical system and updating simultaneously. But again, you're using different types of sensors, there can be latencies and all that. So if the lactate signal is slightly delayed, would the algorithm work? And the answer is no, right? So, and you can simulate that. I'm not going to get into it just for the sake of time. But if you go ahead and turn on the delay variable here, that's going to add a certain amount of delay, which I think I set it as a variable here, but in any case, to the lactate signal and show you that the cyber attack mitigation algorithm is not going to work. So again, this is sort of a very simplistic example, but hopefully you appreciated the power of the tool. So one final thing that I want to say is, well, let's say you integrated all these potential difficulties, nonlinearities into the system and actually came up with a nice mitigation algorithm. Now you want to implement it into a real life system, right? So one thing you can do is, okay, well, MATLAB, it's been real. Let's go back to the real life system, a completely different interface. Try to code everything there and try to make everything integrated. Or you can stay in MATLAB. You can pretty much take your systems box, okay, and this is, I'm going to make it sound like it's super easy, but it's obviously not. But you can technically, right? Zoom out here. So this was your system box. You can take this out and replace it with a real-time interface, right? So, and again, if I go to my library browser here, I can show you some of the available systems. I'm just going to search real time. And this is, I think, well, not, I don't, oh, it may not be installed here. That makes sense. I didn't think of that. But in any case, especially in WSU, we have access to all these toolboxes. So that's great. So it requires a certain toolbox, but basically you can add boxes here, which can do very simplistic stuff such as serial communication with external hardware. Let's say you're running some sort of a microcontroller or some control hardware that can run these algorithms, right? Or that can collect the data and filter it and send it back to you. So you can add those interfaces right here. So the data from the real life can come in, get processed with these algorithms and fed back, right? What you can also do, this is a native functionality, but you can pace your simulation. You can sync it with the real time, right? So obviously this is extremely fast, but you can slow it down such that, and you can add all the flow controls to make sure that it syncs in with your real life application. And you can basically apply what you prototype here directly into your system. Again, takes a little bit of iteration and effort, but it's doable, right? So this is sort of, again, case study, simplistic physical system. There's a lot more complexities that you can add. What is available, it's right there. Hopefully it opens your mind into what are the possibilities when you're going down all the way to the process level and having to deal with cyber attacks and so on and so forth. But if you have any questions, please, we have a little bit of time, I think, to answer them.
Questions for Arda or Brenden?
I don't have a question, but I have a comment, Arda and Brenden. Thank you for a very nice presentation and demo. Arda, you were not around yesterday, but I had given an overview of CySER, and I was trying to give a place for all the presentations that were happening, and I placed yours without knowing the details of it under cyber physical systems, and I was right. And so this is a very good example of what cyber physical systems could look like, and some of the things that are a little different than what was happening so far. So excellent job. Thank you very much.
Thank you, and that makes perfect sense. Yes.
Arda and Brenden will be around for probably a few minutes. Well, Brenden will be around for the day. But if you have any questions, please go up and ask those. Thank you for an excellent presentation. I learned a lot. Of course, it's my area of research, but I'm kind of delving into the cybersecurity aspects along with Arda's help. So really appreciate it.
Thank you.